But I'm kind of surprised, right? Tradition seems to fade away. Then essentially, I have to determine the moduli, which will depend on the dynamic range. I have to have a dynamic range which is large enough to cover my application. Then all the numbers that I want to process can be represented in that system by computing the reminders of the division of the number with those moduli. And then, like in here, 21 is represented like a pair of 4 smaller numbers. And if I want to compute minus x, I do complementation, but it's in the same style of complementation, but I'm not doing complement m. I'm doing complement mi. Then for each channel, we call those RNS channels, I can do the complementation in parallel. You already get an idea, I would say, on the advantages of this approach. There is a parallelization that I'm trying to enable. Instead of processing the entire number, I'm processing the piece apart. You know, the pieces are not connected. And this will allow me to do calculations faster. And we'll see how fast this can be in just a sec. The representation of numbers, it's modulo m. The numbers which are larger than m will actually be represented like numbers which are smaller than m. Then there is an aliasing going on. Then if you will represent a number which is like larger than 840, like 841, that will have the same representation as 1, and so forth and so on. Will that matter? No, because I assumed that in my system, the numbers will go from 0 to 839. Now, this is also a weighted representation, because this is what we like, weighted representations. Otherwise, we get the problem of the Roman numerals. But the weights now are not power of any radix. We'll see later on how those are computed, but there is always a weight on each position, and that weight depends on the position of the reminder, and also on the system. Then in an RNS 753, those are the weights. As you see, the one which appears to be in the most significant position has the smaller weight, which is already suggesting that comparison, it's a kind of tricky thing to do. Now, the beauty of this application is that when I am doing arithmetic on longer numbers, the best thing I can do is to get logarithmic solution for addition. This is what we can do in normal representation. You will see later why this is the case and how do I get that. Are you familiar with asymptotic complexity representations? Like O of 1, O of n, O of log n? Okay. You know, no, yes, that's a kind of fuzzy question, then I have to say something. When we solve a problem, we would like to know how big is the effort to solve that problem. And usually what we do, we say the problem has a dimension, which is n, and then you compute a function f of n, which is representing the number of calculations that you have to do in order to solve that problem. Now, that function can be quite complex, but in the asymptotic notation, we just care for the dominant factor. Then let us assume that I'm solving a problem and f of n, it's equal with n to the power 2 plus n plus, I don't know, a gigantic constant, which might be a billion. In the asymptotic notation, those do not count, and I would say that my solution is quadratic in n, and I would say the complexity is of n squared. If the complexity is linear, and I will write it like an plus b, then it will be O of n. Well, also have O of log n and O of log n, and we also have here things like O of n to the power k, which k is larger than 2. We call that polynomial complexity, linear, logarithmic, and double logarithmic. What we want is to get something which is called O of 1. O of 1 means that doesn't matter the dimension of the problem, I can solve it with the same effort. This will be totally parallel addition, because the delay, the effort that I put in order to do the addition will be the same regardless of the dimension of the operand. We discussed about that kind of addition last time. In addition, what we get standard is O of n. If we do our best, we get O of log of n. Now, if I look at RNS, what I'm trying to do is I'm taking a number, which in binary is representing as n bits, then doing addition on that will require an effort, let's say, logarithmic in n. Instead of trying to do that, I'm doing the following trick. I'm representing the number with that kind of funny representation. And then I have independent channels. Now, because the channels are narrower, then the delay of the addition will now be dominated by the wider channel. Then instead of having an addition which will be logarithmic in n, the addition will be logarithmic in the width of the wider channel. Then basically, what I am trying to achieve is to go towards O log n. That will be my dream. We'll see whether or not we can achieve that. And that's the idea behind RNS. That's the reason why we take the trouble to do some divisions, to compute some reminders, enter another universe, do calculations there because we can do them faster, and eventually return to our universe. So far, so good. Now, one more thing about this kind of asymptotic notation. I forgot to say something about exponential complexity, because we also have things like 2 at power n or k at power n. Those are usually problems which we cannot deal with. Okay? Those are polynomial problems, and those are non-polynomial problems. NP, NP complete, NP hard problems, probably you heard about them, even though you deny that, right? Those are things which we hate. And we usually solve them with heuristics or with quantum computing, if we can. But this is still not a reality. It is very interesting, and it's kind of very attractive way and intellectually challenging way, but it's not yet in place. Now, when we speak about that asymptotic complexity, I just want to finish that because I will not speak again about that. There is a trick. This classification assumes that n is a large number. Then if I deal with databases or with problems which do have a large cardinality, this will always tell me the truth. But if I speak about engineering problems, where the number of bits may be 16 or 32 or 64, sometimes a quadratic solution may be better than a linear or a logarithmic one, depending on the constants. You see, I had here a giant constant, which I didn't take into consideration. But that constant will be dominant in the complexity when n is small. After some time, this can be disregarded. Then if I make here like a graph, let's say this is linear, and this is quadratic, until this point, let's say, oh, this is a bit too optimistic. Then let's say until this point, maybe until this moment, the quadratic solution will be better than the linear solution. But do not quote me on saying that quadratic is better than linear in general. It might be better for engineering instances than when n is small. And this is kind of, you know, this is a corner point when you go for one or the other solution. Are we done with complexity? And from now on, we all know what this, no? Yes, no, maybe. Okay. Now, you see, if I enter RNS, then I can do now arithmetic by having some units which are operating independently. Let's say this is my system, it's an RNS system with modulo 8753. Now, each of those moduli will require a number of bits. Modulo 8 means 0 to 7, 3 bits are enough. Modulo 7, 0 to 6, 3 bits are enough. Modulo 5, 0 to 4, 3 bits are enough. You see here I'm kind of wasting a bit, which I'm using only for one combination. Modulo 3, 0 to 2, 2 bits. Then I kind of use more bits than I should in a normal binary representation. But I may manage to decouple them, and as you see, I take the operands which are partitioned in channels, I fit them to the units, and then I obtain the result. Now, the delay of this addition will be now dominated by the longer channel, which is a 3-bit channel. Then, if I just concentrate on this addition, I won a lot. But as usual, you know, when you move the magnifying glass from one place to the other, you may lose other details. Remember, I had to put some effort to do the conversion, and eventually I would have to put some effort in converting this back to binary because my processor will not understand that. If I do that too often, forget it. If I do it every now and then might be a good thing to do. It's the same story which holds true for binary signed digits and for redundant representations. Now the first question is how to choose the moduli. And now in here there is a kind of trial and error. I have a target dynamic range. Here it's from 0 to 100,000. And I make some choices. And I start, let's say, with, you know, prime numbers, and I take them in a series. I start with 2, which is not a prime number, or it is. It is or it is not? Okay. I was trying to trick you. 4 is not, but 2 it is, even though it is an even number, right? Okay. Then I take those, and you see the product of them is too small. I get the next guy, and then it's too large. And then what I do is I drop 5, and then I get it quite right. Now, there are some things here which I don't like. I don't like the fact that there is a big unbalance between the narrower channel and the wider channel. Okay? Then this will be dominating the addition, while this will be ready very much before that time. And also, I have a lot of channels, maybe too many channels. And what I can do is I can combine some of those channels. Remember, they have to be pairwise prime, not prime numbers, but pairwise prime. And then what I have, it's an RNS with 4 channels. This is not a prime number. This is not a prime number either, but I don't care because they are pairwise prime. I have close to my dynamic range, And then, you know, I have 4 channels which are now better balanced. This is my goal, to have channels which are better balanced and to cover the dynamic range. Now, if you will check, I have 19 bits for this in this representation, which means that most likely I'm using more bits than I would use in a normal representation. Should I take questions?
No, do you?
Should I? Okay, I think it's part of my duty.
Sorry, could you explain what you mean exactly by pairwise prime? Because I thought I got it, but now with 2 numbers that are not prime, I'm a bit confused.
If you divide this by this,
Okay.
or this by this, or this by this, they are pairwise prime. There is no common factor of those 2 numbers. Even though this is 13 times 2, when I divide it by 21, it's not divisible. Okay? Oh, it's good that you asked. I don't mind. I was just trying to cheer you up. You know, it's Monday. Which is also difficult for me, you know. I hope you enjoyed your weekend. Or you worked. You studied computer arithmetic. You struggled with the homework. No? You should have done that, right? For solidarity reasons, I also worked in the weekend. But not in the garden. No. I worked I wrote some papers. Okay. Now I can play different kind of tricks in here. I can also choose things which are powers of smaller primes. Then instead of choosing primes, I'm looking now of powers of primes. My goal is to have channels which are well balanced, not to have very many, and to cover the dynamic range and not more than that, because over-investing does not make sense. Then you see I apply this technique, and now I have different kind of construction. I have slightly larger dynamic range, and I managed to spare 1 bit. Then I got more for less, just by trying to use my brain. I even do some fine-tuning, and you see, I play this, I get now a dynamic range which is too large, and I can drop some of those. And in this way, I can do a lot of kind of tricks and combination until I arrive to my solution. But I also have something else to bear in mind. The fact that I'm doing modular arithmetic, remember, then on each channel, I have to do calculations modulo mi. We remember from complement representation that if I want to compute minus x, I'm doing m minus x. If m is a random number, computing m minus x will cost me an addition. If m is a beautiful number, like 2 to the power k or 2 to the power k minus 1, that will end up in dropping a carry and maybe injecting it back in the least significant position. And that's the reason why we essentially may want to look for powers of 2 or powers of 2 minus 1. And I can play, you know, the same trick here, and I can get a solution which is similar in dynamic range. It's fulfilling my condition. It's larger than 100,000. All my moduli look brilliant. Drop carry and around, drop carry and around, drop carry and around, and I even have less bits. Now, all those things do happen at design time. They cost me brain effort. But if I use my brain, I will win later on. Delay, energy, you name it. And that's your job, right? Whenever you will work in a company or in a university, I don't know what your dreams are, before doing something, you should try to analyze the problem and find the best solution. And best is not mathematically optimal. It's best for the conditions. Okay, there is another trick if I do not manage to do that, I can also go for powers of 2 plus 1, which are not exactly radix complement or digit complement, but I can deal with them with what is called diminished one representation. Then I put an extra bit and I can treat them in a similar way. And they will give me more freedom. Then practically what I want is I want to go for low and moderate cost RNS model. Now we'll see by the end of the lecture whether or not this is helping me to reach my goal. But for the time being, this looks beautiful. Now, if I want to do calculations, I always use that kind of units in a processor to do calculations. And if I want to do that, I want to take the data from somewhere, from the environment, from the memory, from wherever, bring it into my domain of representation, crunch it, and produce the result. Then essentially such an approach will be good if I stay here long enough to win enough to cover the time I spend here and the time I spend here and make a win. Otherwise, I should better go for the standard solution, because the RNS or any kind of signed, aged, redundant, whatever you name it, quantum, if you want, will not pay back. Because I'm making an investment in pre-processing and post-processing in order to get in a domain where I run free. But if that investment is too large, it makes no sense. Now, let us look at the investment. Investment is not as difficult as it may look. Why is that? Because things are well known at design time. Then at design time, I determine the moduli, I know exactly what I'm doing. Then I can make a table, and in that table, I compute the reminders of dividing powers of 2, all the powers of 2 that are of interest for me, by the moduli in my system. Then we have, let's say, from 0 to 9. Those are the powers of 2. And in here I have the moduli of dividing those values by 7, by 5, by 3. That's my system. My system, it's a modulo 8753. Now, if I want to do the calculation, my number is 164. If I want to do the modulo 8 calculation, that's very simple. Because modulo 8 means that I will drop all the bits which do have a power of 2 larger than 2 at power 3. Then if this is my number, then I'm doing modulo 8. This is 16, 32, then 32 will not matter. It's 4 times 8, then it will be out. The same for this. Then modulo 8, it's essentially this guy, 4. For the rest of the guys, I just have to, to look at the bits which I have here and compute, the representation of the number modulo 7 by having the modulo 7 of this element, and of this element. And the same story will hold true for modulo 5 and modulo 3. Then I have to make an effort at design time to generate this table. But this is energy free, because it's something which I run offline. It's not in place when my system is running. Then what I have to do is I have to make some lookups based on the bits which I have in my number. I bring values from the table, and I do a number of additions, and those additions are modulo the weight of the modulo in that channel. Then making a conversion is not that difficult after all. I'm not doing division. Normally, if I think, you know, I just follow the book of the RNS representation, I'm saying 164 divided by 8 will give me a remainder of 4. Then I make a division. You don't do that. That's simple. For 8, it's just trivial. For 7, I don't divide by 7 and get the remainder. I do 3 lookups, addition, modulo. And then instead of doing divisions, I'm doing additions, modulo mi, and I do them also in parallel. Then the effort is not that bad. Because if you look at the definition of the system and you see division, you immediately get scared. But I managed to hide the division in such lookups and additions. Now, because this system has a funny kind of weighting, you know, each position has a weight, but they are not ordered, I cannot really compare numbers in their format. I have 2 solutions. One, it's to convert them back in binary, compare, and then make a decision. Remember, each and every 5 instructions, you may have a branch in a normal processor, which means that solution is not good. And anyway, this is not an approach which will function for that kind of programs. Then this is mainly for addition, multiplication dominated applications like digital signal processing. Because if I want to execute general purpose programs where a block of instructions have about 5 instructions on average, which end with a branch, which might be branch on whatever, something which will require a comparison, I don't win. Now, another solution is to make a step towards a conversion, but not to binary or to decimal, to make a conversion which is kind of easier in another system which is called mixed radix. Then instead of representing the number in RNS or in binary or in decimal, you represent it in a system where you have weights starting from 1 up to the product of all the moduli. You see they are ordered. Then the first digit is the one which has the heaviest weight because it's the product of all the moduli. The second is lighter and lighter and lighter until the first one has a weight of 1. Then if I make a conversion from RNS to that radix, I don't have in here the conversion, but you have it explained in the book, how that is done. And it's well explained. It's not unclear. Okay? I can get a way to compare 2 numbers without going in binary. Then you see, I have an example here. I have 48 versus 45. If I look at the representation in RNS, and I try to use my instinct, which will tell me that if the most significant position is larger, that number is larger, I'm wrong. Because this is 48, this is 45. By the nature of the calculation, this property does not hold true. However, if I convert those numbers from RNS to the mixed radix representation, you see now I can do the inspection. 0310, 0300. This is larger, as it should. Then I have to make an effort to make the conversion from RNS to this mixed radix, and in this mixed radix I can see which one is larger. Actually, when I'm doing the conversion, I can also tell that. While converting, I can also do the comparison. And this is one way to do chip conversion. The other way is based, because the thing was coming from Sun Tzu, the most important result in RNS is called the Chinese remainder theorem. Looks ugly, right? Are you scared of this formula? I saw some faces which were looking like, Okay, the Chinese reminder theorem is helping us to solve Shunzu's puzzle. And it may look very difficult, but in practice is not that difficult. You don't have to prove this theorem. Neither do you have to understand the proof. You just have to understand how this is working. And essentially this is working in the similar way. This is now conversion back. Conversion back relies on the same kind of trick. I know my system is fixed, right? I can make a table, and in that table I have all the numbers that I need. I do some lookups, I do additions, and what is different from before is that now when I do the calculation, the final step, it's a modulo M operation. Now, then essentially you compute a sum where you have, you have to compute MI, capital MI, which is now the product of all the moduli but the moduli in the current position. Do I have to compute it online? No, because this is fixed. My system is fixed, then this can be computed beforehand. Alpha I is the multiplicative inverse of mi to respect with small mi. This is also constant. I'm computing it offline. Now, because they both take part of this calculation, I compute them, and then I also compute this product, and I do it modulo mi. X, it's my digit, my RNS digit. But also that one is fixed. If my mi is 8, x can be from 0 to 7. And I can include all of those in this table. Then everything that I need in order to evaluate that, I have it in a table. Then practically, if I have 4 channels, I have to do 4 lookups, get those golden numbers, add them, and do modulo M calculation. From the mathematical point of view, may look ugly. From the computational point of view, it's kind of simple. Lookup, no problem. If I want to have parallel calculations, I make a memory from where I can read 4 values in the same time. I just need 4 read ports. Then such a memory will not be very ugly. I'm not writing in that memory. Never, because things are not changing. My system is fixed. Then I have 4 channels, my memory has to have 4 ports. If I don't have 4 ports, I make, the read in a serial fashion. Will it be bad to have 4 ports to that memory? What will be the implications to have 4 ports in such a memory? Microelectronics. You are not from microelectronics. You always want to answer. This is something microelectronics people should know. Oh my God. Nobody from microelectronics is here, right? No, that's a good excuse not to answer and to let him answer.
I'll try.
No, you say. Do I care?
Well, you might not, but people who might care.
No, you will not care either, because today area is commodity. We have more transistors than we can use. That's true. Have you ever heard about black silicon? Black silicon is silicon which I have on the chip, and essentially I don't know what to do with it. Yes?
Due to the time constraints, you have to answer to the 4 ports in a time constraint.
Then you will have a problem with the access time.
Yeah.
I hate you. No, actually, I like that you answered. I'm just trying to tease the people which should understand, the inside of the memory. Because you have more channels, you will have a more complex access logic, and that might increase your cycle time. Might. You are not sure. This depends on the design. But basically what you would like to do here is to read all of them in parallel, do the addition, and now you have the problem. Now is coming the complexity, because that has to be done modulo m. M, it's a large number, and is not any longer a beautiful number. It's the product of all the moduli. Then that might require some kind of subtraction.